Hi friends, in the last video we have seen what is a p-type and n-type semiconductor, right? Now we'll see what is a p-n junction. Start with a p-type conductor and add precisely a small quantity of pentavalent impurity. Then some part of this material will turn into n-type. First it was p-type. Because you have added a pentavalent impurity, this part can turn into n-type, and that is what you are seeing. This is known as p-n junction. Now you know that p-type has more number of holes, that is positive charge dominant, and n-type has more number of electrons, right? Free electrons, that is conduction electrons. Concentration of electrons is more. Because of this what? Concentration gradient, that is here the holes are more and here the electrons are more. Because of this concentration differences, what happens? The holes tend to move to the right side, that is towards the n side. As you observe, some are moving right, and some of the electrons tend to move to the left side, that is to the p side. And since this motion happens, you know that moment of charges gives current, right? There is a current here. Since positive charges are moving in this way and negative charges are moving in this way, this current will be in this direction, and this current is known as diffusion current. And because of this diffusion current, there will be some charges accumulated. Are you seeing these symbols? Because the holes are moving towards the right, they get accumulated on the n side, and similarly electrons get accumulated on the p side. Hence here there is some accumulation of charges in the middle. This region is known as depletion region. It is of the order 10 power minus 7 meters. It is very less. That is why we have started with a p-type material and added some impurities to make a part of it n-type, right? Now why can't we join a p-type material and n-type material and take two slabs and just join them physically? This is wrong. We can't get a p-n junction with that, because if we join physically, the distance between these two types, that will be far more than what it is in this case. So that's why you can't get it just by adding two slabs physically. Because of this diffusion current, there are some charges accumulated here, right, in the depletion region. Now because these charges are accumulated, there is a potential difference between these two points, or these two places, or these two ends. And this potential difference gives rise to electric field, or other way of saying is that there are positive charges accumulated here, right? So they attract electrons. That is, these positive charges attract these electrons back, and these negative charges accumulated attract these accumulated that is these diffused positive charges back. So there is again a reverse motion. You just understand it. Because of these accumulated charges in the depletion region, there is an electric field, and so the charges are moved back to their home semiconductor. That's it. And because of that, electrons are moving again in this direction. Of course, this will be very little, and holes are moving again in this direction towards the p. And so this also gives rise to a current. This is opposite to diffusion current. This is known as drift current. So initially there was nothing. There were more holes here and more electrons here. Because of that, some holes started moving here and some electrons started moving here. That is first thing to understand. And next, what happened? Because of this movement, some charges got accumulated here. Some positive charges here, that is holes, and some negative charges here. And because of this accumulation, there was an electric field, and that gave rise to motion of electrons again in this direction, and holes again in this direction back. That gave rise to something called as drift current. That is what you have to understand. Now you have two currents, right? Two opposite currents, that is diffusion current and drift current. Now which will dominate? Actually, in equilibrium, diffusion current will be equal to drift current. That is what we call as equilibrium. So under equilibrium, there is no current at all. This potential which you see in the depletion region, it tends to prevent the movement of electrons from n-type region to p-type region. So it is called as barrier potential. One more important term to remember. A diode is nothing but a p-n junction with metallic ends. That's it. These metallic ends are connected to a battery or any potential difference. That is what is our idea, to get some potential difference between these two types, P type and N type. Well, they can be connected in this way or this way also. And of course, there are two types here. That's what we call as forward bias and reverse bias. Let's discuss them in detail. For now, you note that this is the symbol of diode. The arrow or the triangle points from P to N, P type to N type, and this is how it looks physically. This is how they look when placed inside a circuit. And observe that here there is a diode, here there is a diode, and there may be some other diodes also which I'm not able to see. Let's move forward. When P type of the PN junction is connected to the positive plate, that is plate with higher potential, and N type is connected to the plate with lower potential, that is known as forward bias. Most of the potential that is applied externally, that drops in this region only, because this material or the semiconductor material that has not much appreciable resistance, so much of the potential drops in this region only, in the depletion region. Now note one thing, because of this battery, this point is at higher potential than this, right? So first of all, there was some barrier potential inside this PN junction. It was in this way. Higher potential was, that is, positive charges were accumulated at N side, right? So this was the barrier potential V naught. Now, because of the external voltage applied, this is at higher potential than this. So here it is something like this. Observe it. They are opposite. That's what I want to say. This is the external voltage. So finally, what can I say? The net barrier has been reduced. Are you getting me? The net barrier has been reduced, and so you see that the barrier width, this one, it has been reduced. Are you able to observe? The barrier height is reduced, or you can say that this depletion region width has been reduced. And so what happens now, since this barrier is reduced, now electrons are able to reach the other side easily, because the barrier's height is reduced now. And similarly, the holes also can reach this side easily, and electrons can reach this side easily, because this has been reduced, the barrier has been reduced. Now, if the external voltage applied is small in magnitude, then what happens? Only little part of it is reduced, little part of it is reduced. So only some electrons which have higher energy can reach the other side. Similarly, holes also. But if applied external voltage is very large, say, that is, then what happens? Much of the barrier is reduced, right? So now the barrier height is very less. That is, the potential difference between this at this depletion region is very less. So almost all the electrons can reach the other side, and similarly holes also. What happens? It results in increase in current, right? So more the external voltage, more will be the current, and less the external voltage, less will be the current. And note that this current will be in this direction, forward direction, that is P to N. So P to N is the current direction, because electrons are going in this way, right, from N side to P side. Because of the reduction of barrier height, electrons are able to go in this way, and holes are also able to go from P to N. Now note one thing, electrons are going from N to P, where in P type, electrons are minority charge carriers, right? So they are going to a place where they are minority charge carriers. Even if it is the case with holes, holes are going to N, and N is the place where holes are minority charge carriers. In both the cases, the charged particles are going to those places where they are minority charge carriers. That is why this is called as minority carrier injection. And note that the total diode forward current, it will be the sum of hole diffusion current as well as electron diffusion current. Note that, of course, the magnitude will be very, very less, somewhere in milliamperes. We'll go to the next case, that is reverse bias. Reverse bias is just the opposite case, where P type is connected to the negative terminal or the terminal with lower potential, and N type is connected to the that terminal with higher potential. The barrier potential was in this direction, right, V naught. And note that this is at higher potential given by the battery. So the applied external voltage also in this way. So the net barrier potential will be V plus V naught. That is, barrier height has been increased and it is even more difficult now for the charges to go to the other side. And that is why you see that the width of this depletion region has been increased. Now, of course, electrons can't go to the p side, but what happens adding to it, if any diffused electron that is in this region, say, even that electron, when it comes to this depletion region or close to this depletion region due to random motion, even that is pulled back to its n side. Similarly, if any hole which has been diffused before into the n-type region, if it comes close to the depletion region, even that is pulled back to its p-type region. So this motion of charges gives some current, right? This is electrons are moving in this direction and holes are moving in this direction, right? So the net current direction will be in this way, opposite to that we saw in the forward bias. So this is known as drift current. The drift current here will be even more less than what we saw in forward bias case. Here it will be in microamperes. There at least it was in milliamperes. Why is this so less? And one more thing is that this drift current doesn't depend on the external voltage applied. Whatever voltage you apply, it is enough to bring all the diffused particles back to their respective types. Now, why is this so? Because actually it is not limited by the applied external voltage. It is limited due to the concentration of minority carriers. That is, first of all, what happens here? The holes are coming back, right, which are diffused before. That number of holes are itself very less because they are in n-type region. Note that. And similarly, the electrons which were diffused are coming back, but the number of electrons which are diffused itself is very less, and hence whatever voltage you apply, even though it is very small, that's enough to bring all of them back to their respective homes. And that is why this drift current is very less and it is not affected by the external voltage. But if you increase the potential difference too much in the reverse direction, there is something called as breakdown voltage. You observe this. This is the graph that gives the nature of the diode, that is how it reacts with potential difference. Now, if you reverse the potential difference and increase in magnitude too much, there comes a breakdown voltage VBR, beyond which the current increases exponentially, that is too much, and actually because of this there will be too much of current in the circuit and the diode gets what burnt out. Not only here, even in the forward bias case, if you increase the potential difference too much, that is there is something called as VD, or it is also called as threshold voltage. Beyond that, there will be too much of current, and if current is too much, then more heat generated in the circuit, more heat will be generated, and so the diode is destroyed even here. So this is how a diode reacts with external voltage applied. Now, what is the resistance of diode? As you see, this is current and this is voltage, right? The slope, it gives di by dv, so the reverse of the slope, that is dv by di, which should be the resistance according to Ohm's law. And that's why we have something called as dynamic resistance when it's the case with diodes, because static means something constant which doesn't change with time. Dynamic means it is moving, that is it is changing actually. Here the dv by di, it will be changing with the potential difference or with the current. So at each point you have a different resistance. If you want to calculate the resistance at a point, you have to take the respective values those are near to your situation. Say, solve this example. This is a silicon diode, say, and say at one point the current, diode current was 15 milliamperes at this point, and say it was 20 here and 10 here. If it was say 0.7 volts when it is 10 milliampere, and if it was 0.8 volts when it is 20 milliamperes, then my resistance, dynamic resistance will be, it will be 0.1 by 10 milliamperes, right? 10 power minus 3. That should give me 10 ohms. So it is 10 ohms at at diode current 15 milliampere.